Article 250.142 within the National Electrical Code addresses the integrity of the equipment grounding conductor and its relationship to the neutral conductor in electrical systems. The core principle established is that the equipment grounding conductor shall not be used as a neutral conductor. This prohibition stems from fundamental safety considerations and the proper functioning of electrical distribution networks. To understand this, it is crucial to differentiate between the functions of the neutral conductor and the equipment grounding conductor. The neutral conductor, in a balanced three-wire system or a Y-connected system, serves as the return path for current under normal operating conditions. It carries the imbalanced load back to the source. In contrast, the equipment grounding conductor provides a low impedance path for fault current to return to the source, facilitating the rapid operation of overcurrent protective devices such as circuit breakers or fuses in the event of a ground fault. This low impedance path is essential for minimizing the duration of fault conditions and reducing the risk of electrical shock hazards. Connecting the neutral and equipment grounding conductors at points beyond the service entrance creates multiple current paths for the neutral current. This can lead to undesirable consequences. Firstly, current will flow through the equipment grounding conductors, which are not designed to carry continuous load current. This can cause the grounding conductors to overheat, potentially damaging equipment and increasing the risk of fire. Secondly, the presence of neutral current in the equipment grounding system can introduce objectionable voltage on metal parts of equipment and raceways. This can create a shock hazard for personnel who come into contact with these surfaces. Thirdly, the impedance of the equipment grounding path is typically higher than that of a dedicated neutral conductor. This can result in voltage drops and poor voltage regulation, affecting the performance of sensitive electronic equipment. The National Electrical Code provides specific requirements for grounding and bonding to ensure the safety and proper operation of electrical systems. These requirements are designed to prevent ground faults, minimize the risk of electrical shock, and ensure that overcurrent protective devices operate correctly. The separation of the neutral and equipment grounding conductors is a fundamental aspect of these requirements. In a separately derived system, such as a generator or transformer, the neutral conductor must be grounded at the source. This grounding connection establishes a reference point for the system voltage and provides a path for fault current to return to the source. The equipment grounding conductors must be connected to the grounded neutral at the source, creating a low impedance path for fault current. The equipment grounding conductors must also be bonded to all metal parts of equipment and raceways to ensure that these surfaces are the same potential as the grounded neutral. This bonding minimizes the risk of electrical shock hazards. The National Electrical Code also specifies the types of conductors that can be used for grounding and bonding. Equipment grounding conductors can be either bare or insulated. If insulated, they must be identified by a green color or a green color with one or more yellow stripes. Bonding jumpers, which are used to connect different metal parts of equipment and raceways, must be made of copper or other corrosion-resistant material. The size of the equipment grounding conductors and bonding jumpers must be based on the size of the overcurrent protective devices in the circuit. The National Electrical Code provides tables that specify the minimum size of these conductors. In addition to the general requirements for grounding and bonding, there are also specific requirements for certain types of equipment and installations. For example, the National Electrical Code specifies the grounding requirements for swimming pools, spas, and hot tubs. These requirements are designed to minimize the risk of electrical shock hazards in these areas. The National Electrical Code also specifies the grounding requirements for sensitive electronic equipment, such as computers and medical equipment. These requirements are designed to protect this equipment from damage due to voltage surges and other electrical disturbances. It is essential to comply with the National Electrical Code requirements for grounding and bonding to ensure the safety and proper operation of electrical systems. Failure to comply with these requirements can result in serious electrical shock hazards and equipment damage. Article 250 within the National Electrical Code covers grounding and bonding comprehensively, with Section 250.142 specifically focusing on the impermissibility of using the equipment grounding conductor as a neutral conductor. To elaborate further, let's consider the practical implications of violating this code requirement. Imagine a scenario where the neutral conductor of a lighting panel is inadvertently connected to the building's grounding system. Under normal operating conditions, the neutral current, which is the current returning from the lighting loads, would flow through the building's grounding system. This means that the metal enclosures of electrical equipment, metallic conduits, and even structural steel within the building would become energized with the neutral current. This situation creates a significant safety hazard because anyone who comes into contact with these metal surfaces could experience an electrical shock. The severity of the shock would depend on the magnitude of the neutral current and the resistance of the person's body. Furthermore, the flow of neutral current through the grounding system can interfere with the proper operation of sensitive electronic equipment. The grounding system is designed to provide a stable reference potential for electronic devices, but the presence of neutral current can introduce noise and voltage fluctuations that disrupt their performance. This can lead to data errors, equipment malfunctions, and even permanent damage. In addition to the safety and performance issues, using the equipment grounding conductor as a neutral conductor also violates the fundamental principles of electrical system design. The neutral conductor is intended to carry current under normal operating conditions, while the equipment grounding conductor is intended to carry current only under fault conditions. By combining these two functions, you are essentially overloading the grounding system and compromising its ability to protect against electrical hazards. The National Electrical Code provides specific requirements for the size and type of conductors that must be used for grounding and bonding. These requirements are based on the expected fault current levels and the need to provide a low impedance path for fault current to return to the source. By using the equipment grounding conductor as a neutral conductor, you are likely to be using an undersized conductor that cannot safely handle the expected fault current. This can lead to overheating, insulation damage, and even conductor failure during a fault condition. To avoid these problems, it is essential to ensure that the neutral conductor and the equipment grounding conductor are kept separate and distinct. The neutral conductor should be connected to the neutral busbar in the electrical panel, and the equipment grounding conductor should be connected to the grounding busbar. These two busbars should be bonded together only at the service entrance or at the source of a separately derived system. In existing installations where the neutral and grounding conductors are inadvertently connected, it is necessary to correct the wiring to comply with the National Electrical Code. This may involve running a separate neutral conductor to the lighting panel or reconfiguring the grounding system to ensure that the neutral and grounding conductors are properly isolated. It is important to note that the National Electrical Code is a complex and comprehensive document that covers a wide range of electrical safety topics. This explanation is intended to provide a general overview of the requirements for grounding and bonding, but it is not a substitute for consulting the National Electrical Code itself. If you have any questions or concerns about electrical safety, it is always best to consult with a qualified electrician. In the context of a 277/480 volts Y system, the importance of maintaining separate neutral and ground conductors is amplified. These systems are commonly used in industrial and commercial facilities to supply power to lighting, motors, and other equipment. The high voltage levels in these systems increase the potential for electrical shock hazards, making proper grounding and bonding even more critical. In a 277/480 volts Y system, the neutral conductor is typically grounded at the service entrance or at the source of a separately derived system. This grounding connection establishes a reference point for the system voltage and provides a path for fault current to return to the source. The equipment grounding conductors are connected to the grounded neutral at the source, creating a low impedance path for fault current. If the neutral and grounding conductors are inadvertently connected downstream from the service entrance, the neutral current will flow through the equipment grounding conductors, energizing metal parts of equipment and raceways. This can create a significant shock hazard, especially in environments where workers are exposed to wet or damp conditions. In addition to the shock hazard, the presence of neutral current in the grounding system can also interfere with the operation of sensitive electronic equipment. Many industrial and commercial facilities rely on sophisticated electronic controls and automation systems to manage their operations. These systems are often sensitive to voltage fluctuations and electrical noise, which can be caused by neutral current flowing through the grounding system. To prevent these problems, it is essential to ensure that the neutral and grounding conductors are kept separate and distinct in 277/480 volts Y systems. The neutral conductor should be connected to the neutral busbar in the electrical panel, and the equipment grounding conductor should be connected to the grounding busbar. These two busbars should be bonded together only at the service entrance or at the source of a separately derived system. It is also important to ensure that the equipment grounding conductors are properly sized and installed. The size of the equipment grounding conductors must be based on the size of the overcurrent protective devices in the circuit, and the conductors must be installed in a manner that provides a low impedance path for fault current to return to the source. In some cases, it may be necessary to install supplemental grounding electrodes to improve the performance of the grounding system. Grounding electrodes are metal rods or plates that are buried in the earth and connected to the grounding system. These electrodes help to dissipate fault current into the earth, reducing the voltage on metal parts of equipment and raceways. The National Electrical Code provides specific requirements for the installation of grounding electrodes. In summary, the prohibition against using the equipment grounding conductor as a neutral conductor is a fundamental safety requirement in electrical systems. This requirement is based on the need to protect against electrical shock hazards, prevent equipment damage, and ensure the proper operation of electrical systems. By complying with the National Electrical Code requirements for grounding and bonding, you can create a safe and reliable electrical environment for your facility. Remember that electrical work should only be performed by qualified and licensed electricians who are familiar with the National Electrical Code and local electrical codes. Improper wiring can create serious safety hazards and lead to costly repairs. When you run a new service to the lighting panel, be sure to adhere strictly to the National Electrical Code requirements for grounding and bonding. This includes installing separate neutral and grounding conductors, properly sizing the conductors, and bonding all metal parts of equipment and raceways. By taking these precautions, you can ensure that your electrical system is safe and reliable. Furthermore, consider the implications of using a 3-wire system versus a 4-wire system. A 3-wire system typically consists of 2 hot wires and a neutral wire, while a 4-wire system consists of 2 hot wires, a neutral wire, and an equipment grounding conductor. In a 3-wire system, the neutral wire is often used as the equipment grounding conductor, which can create the safety hazards described earlier. A 4-wire system provides a dedicated equipment grounding conductor, which eliminates the risk of neutral current flowing through the grounding system. When you run a new service to the lighting panel, consider using a 4-wire system to improve the safety and reliability of the electrical system. This will require installing a separate equipment grounding conductor and bonding it to all metal parts of equipment and raceways. While a 3-wire system might appear simpler or more cost-effective initially, the long-term safety and performance benefits of a 4-wire system far outweigh any perceived advantages of the 3-wire configuration. Prioritize safety and code compliance when making electrical system modifications. If the existing lighting panel is wired with a 3-wire system where the ground is being used as the neutral, it's crucial to address not just the new service, but also the existing wiring within the panel and downstream circuits. Simply running a new 4-wire service to a panel that still has internal wiring using the ground as neutral won't fully resolve the safety issue. Here's a breakdown of considerations for rectifying the existing wiring. Firstly, identify all circuits within the panel that are using the ground as neutral. This will likely require a thorough inspection and tracing of each circuit. Secondly, rewire each identified circuit to separate the neutral and ground conductors. This typically involves running a new neutral conductor to each lighting fixture or device and connecting the existing ground wire to the equipment grounding terminal. Thirdly, ensure proper grounding of the panel itself. The panel enclosure must be properly grounded to the building's grounding electrode system. This ensures that the panel is at the same potential as the earth, reducing the risk of electrical shock. Fourthly, use appropriately sized conductors for both the neutral and ground wires. The conductor size should be based on the ampacity requirements of the circuit and the National Electrical Code guidelines. Fifthly, properly terminate all conductors at the panel and at the lighting fixtures or devices. Use appropriate connectors and ensure that all connections are tight and secure. Sixthly, test the system after rewiring. Use a multimeter or circuit tester to verify that the neutral and ground conductors are properly isolated and that there are no unintended connections. The absence of a dedicated neutral can lead to harmonic currents circulating on the ground. Harmonic currents are multiples of the fundamental frequency of the alternating current, typically 60 Hz. These currents can be generated by nonlinear loads such as electronic ballasts in lighting fixtures and variable frequency drives. When harmonic currents flow through the grounding system, they can cause overheating of conductors, voltage distortion, and interference with sensitive electronic equipment. In a system where the ground is used as the neutral, the harmonic currents will flow through the building's grounding system, potentially affecting other equipment and systems. By separating the neutral and ground conductors, you provide a dedicated path for the neutral current, including harmonic currents, to return to the source. This reduces the risk of harmonic currents circulating on the grounding system and causing problems. When selecting a new lighting panel, consider using a panel with a separate neutral and ground bus bar. This will make it easier to wire a panel correctly and ensure that the neutral and ground conductors are properly isolated. The neutral bus bar should be insulated from the panel enclosure, while the ground bus bar should be bonded to the panel enclosure. Proper grounding and bonding are critical for the safety and reliability of electrical systems. By following the National Electrical Code requirements and best practices, you can minimize the risk of electrical shock hazards, prevent equipment damage, and ensure the proper operation of your electrical system.